So that's kind of the big picture intro to partitioning, which really is a critical process that goes on inside the model. So these are the different processes that are being accounted for by the EFDC toxic submodel. So, this is the sediment bed. Then we have some kind of bottom of the sediment bed, hard rock, whatever it's the bottom of our sediment layers in the EFDC. Water column here, and you have partitioning processes going on in the sediment bed, which are unique to the partitioning processes that are going on in the water column, because your temperatures may be different, your pHs ultimately may be different when we get to that. Your organic carbon content will almost assuredly be different between what's in the water column versus what's in the sediment bed. So, but everything in EFDC kind of works off it basically tracks total toxics in the bed at a layer, and in the water column in a cell, and a layer in the cell. And then we'll talk about this a little bit later about what they call the fractional solution technique. Then it transports, and then it starts splitting stuff up into the different units, fractions. But so we've got the partitioning, and we also have associated with that, as it partitions to a particulate bound material, it can settle. Likewise, the contaminant that's bound to a sediment particle, if it gets resuspended, gets kicked up into the water column. We have pore water diffusion in bed mixing, not so much into the water column so much as in the sediment bed here, but you do have pore water diffusion occurring both inside the bed between the layers, and then there's a separate pore water diffusion coefficient for the bed water interface. So you have diffusion processes in the sediment bed, and then at the sediment water interface. External loads. You have the ability to assign a groundwater flux term at the bottom and add a groundwater concentration, which will in turn advect and diffuse that contaminant through the sediment bed to the water column and out to the water, out into the water column, if that's a concern. Most of the time, this sediment bed actually acts as a zero flow boundary. So there is nothing coming in, but you can put in a groundwater flux and a concentration associated with it. Let's see. The mixing component, there's a bioturbation / mechanical disturbance depth and a diffusion rate that you can specify in EFDC, and it'll mix not just the water, it actually mixes the particles, and will smear out any kind of like a front or something in the near surface. Typically, this mixing depth corresponds to your bioturbation depth, which is anywhere from 5 centimeters to maybe 15 centimeters. But it could be more, could be less, could be 0. But it's it's an optional input, but it actually mixes the bed particles, not just the pore water. And anything else? Reactions, yeah. We've got in the new EFDC Plus now, we've added the loss terms, so we'll talk about those, but you have a different set of rates and processes in the sediment bed versus what's in the water column. And then in the water column, you have a loss term here, volatilization. if the parameter volatilizes, it will, and we'll cover that later too. We don't have photolysis in here yet. Just curious, has anybody needed to use or have used photolysis in any of the work that anybody's done? What's that? Yeah, I mean, I expect to add it probably as 8.4, but it's just not in there now. Got to step it forward. Hydrolysis is the same thing, but hydrolysis is dependent upon the redox, so we need pH before we can do hydrolysis. So it's the same issue, step by step. Let's see, anything else? Obviously, advection, dispersion, all your forcings, your hydrodynamics are fully operating up here, moving material around according to the all your boundary conditions. And I think, oh, well, I didn't. Yeah, that's a good point. Yeah, this is optionally 3-phase partitioning. You can have, there's a 1-phase, a 2-phase partitioning, and 3-phase. And what 1-phase partitioning is it's, you can have the dissolved material strictly bound to a particulate. That's the KD approach. So it's just a 2-number, you got the total and the dissolved. And that partitioning. That's an option. Another option is you can, I can have partitioning and then bound to a particulate here that is a fraction of organic carbon. That's also still essentially 2-phase partitioning, but the partitioning coefficient varies with organic carbon. And then optionally, you can sorb a fraction of the dissolved to dissolved organic carbon. Now, it is partitioned to a material, but that material is dissolved. So they both act as dissolved, and you'll see that in the equations. So whenever you look at the transport equations, you'll have the dissolved phase plus the fraction that's absorbed to the dissolved phase. And that basically constitutes your 3-phase partitioning, where you have truly dissolved bound to a dissolved component, and then particulate bound. So 3-phase partitioning. And it applies both in the surface and in the sediment bed. So, let's see. You'll see a lot of subscripts and superscripts, and I'll just describe them here on this page and then probably ignore them thereafter. Here's the 3 different ratios that are important for this process. This is the fraction of truly dissolved to the total. And that's equal to this ratio here of the 1 divided by the 1 being the mass associated with the dissolved phase. This is the number that represents the mass associated with the partitioning onto solids of class I solids. So the I represents the sediment class. So every sediment class has its own concentration. And then over here you've got, this is the fraction of the solid, or the constituent that is attached to the dissolved phase. So this is the partitioning coefficient to the dissolved phase organic carbon, or DOC. Although this refers to a class of DOC of J, I don't know of any other DOC except for total dissolved carbon that's ever been used. There might be some special case where you've got multiple other dissolved constituents, but this is written so that you could have multiple ones, but actually the code really only allows for one dissolved phase, and it's a DOC, a dissolved organic carbon. So that's your denominator here, which is fractionally equal to the mass of your total mass in the unit volume here. So then you just look at here's the amount of mass that's absorbed to the dissolved phase, organic carbon, and then likewise the mass that's absorbed to the solid phase. Let's see, anything else? Nope. Oh, just the units here, cubic meters per milligram. That converts to your pretty much standard liters. Actually, that's supposed to be cubic meters per gram. It converts to your liters per milligram, which is a very typical unit when people are reporting partition coefficients. Yeah, and this product is dimensionless. I think that's enough for that. Now there's some kind of unique things about the way EFDC Plus has implemented some of this partitioning. Conceptually, this is the approach, but how this is actually implemented in the code and your options that you have available in EFDC Plus are kind of, you might say there's a couple of special cases. For one thing, prior to EFDC Plus, toxic contaminant number 1 controlled all the partitioning options for all the toxics. So it would apply one partitioning that you had specified for toxic 1 to everything. You could have different coefficients, but the approach was set by the first toxic. With EFDC Plus now, every toxic can be its own unique partitioning approach. You don't need to have the same approach for all the constituents in a run. Secondly, dissolved organic carbon is not a constituent that is simulated directly in EFDC in the toxics model. It is supplied externally as an input to the processes going on in the model. And there are a couple of ways you can do that. You can enter a single value of a DOC that's temporally and spatially constant, or you can use a spatially varying file, POCW, and DOCW, and vary your dissolved organic carbon spatially in the model domain. So you have, but this has to be explicitly specified by the user if you're going to use it. Also, with respect to particulate organic carbon, there's 3 different ways that you can obtain that POC value to be used in your partitioning. The first, well, one of them is you ignore it and you use the KD approach. The second approach is if you ignore organic carbon, you essentially end up with KD. If you don't ignore it, then you have to specify the fraction of organic carbon for each size class in the water column and in the sediment bed. I think this probably is the most general and useful approach most of the time, because you've already got a sediment transport model, and it's kind of, you got it kind of nailed down when you get to the toxics. So here what you're doing is you're just saying, okay, well, of that inorganic or of that cohesive material out there, 20% of that is organic carbon, and then that inorganic, I mean that non-cohesive sediment class, maybe 5% is organic carbon, etc. And all you have to do is assign these FOCs, and they will be applied when it's calculating the POC. You do have an option for spatially varying your FOCs associated with your sediment classes also. Again, a different option, but it's essentially just kind of, from the standpoint of the partitioning, it's the same thing as this. It's just that it's spatially varying instead of fixed by class. And then finally, you have an option where you actually just explicitly specify a POC value, either spatially constant or spatially varying. And this one, yeah, I've never used it. I'm not sure. Earl, have you ever used it? Yeah. I'm not sure exactly why you'd necessarily want to do that, because you've got good TSS out there, then I guess maybe that's actually why you'd possibly use it if you didn't model TSS, which we always do, so I don't know. But anyways, it's possible to do it in where it's just externally specified organic carbon, particular organic carbon. So that, all of those different options basically, feed into how this partitioning process will happen, where it gets its S, and D values here for the, well, actually the P values in this equation here for the partitioning. So, a simplified version of the toxics transport model or approach in EFDC. It's essentially the same as all the other transport equations. Surprise, surprise. The difference here is with the solids, we had a settling velocity, and then we had the settling term here, but here we're associating that fraction of the solid for that particular size class, for that particular settling velocity, moves the mass of toxic with the sediment as it settles. And then on this side over here, you've got your source and sink terms for your internal and external links, and these external being boundary conditions, atmospheric loads that are coming in. Atmospheric loads are losses from volatilization, but that would be your external, and then your internal source and sink would be any kind of biodegradation, degradation, or conversions, which can go plus and minus when look to add kinetic processes that allow for change of state. So things can go from maybe one toxic and degrade to another toxic, but they don't degrade totally out of the system. They just change their the nature and change their properties. So if you had that kinetic process parameterized, it'd be a loss from one constituent, but a gain from another. That process right now is not in EFDC plus yet. The transformation and kinetic process from one state to another. I hope 8.4. Got pinning a lot of stuff on 8.4. Yep. So you've got this advective diffusive equation. So the way EFDC solves that equation is the first thing it does is it uses the dissolved phase transport with your external sources and sinks. And it goes through the advection step, advection diffusion step. So and that's, you might call it, I think it's in the documentation, it's like N plus 1/4. And that, so you finish with your advection diffusion step. And at the end of that process, then you apply a settling process. And now material in the system that at the end of the advection diffusion step is now settled with the particulates that would have settled. Then you add a deposition resuspension step down at the bottom layer between the sediment bed and the water column, and move mass either from the water column to the bed or vice versa, and go through that process. And then you have pore water advection and diffusion. So as things are moving up through the bed, or you have a losing system and it's going through the bed downward, that process is then solved. And finally, any kind of kinetic processes, reactions, internal losses, etc., is the last step in the solution scheme. So when that gets finished, the time step for the toxics is finished. So just kind of looking at some of the equations. So settling, again, we're kind of picking up the settling of the solids as it moves down through the water column. And the sign convention here assumes that your settling velocity, this term becomes negative, because this is your layer above. So your concentration of your layer above is, as it moves down, the settling obviously removes mass from the layer above and adds it to the mass from the layer below, or to the layer below. So anyways, that's the basic settling equation. Of course, again, you've got your standard partitioning approach here. Notice your partitioning, all up here, this is strictly to solids. There's obviously no dissolved phase shown up here, because it's not going to settle. So the erosion deposition step affecting layer 1. So here, your units are in grams per meter squared. This is your total mass in grams per meter, or milligrams rather, for toxics. This is milligrams per meter squared, and this is milligrams per meter squared. Because the C here is assuming that you're using a unit mass concentration. So it's a milligrams per kilogram, or in this case, actually, it's, milligrams per kilogram of toxics. Then you multiply it times the bed mass to get the milligrams of toxic per square meter of the sediment bed. And then this is the height of the layer 1 times the concentration and depth, so you end up with the same units. So this is you end up with milligrams per meter squared, and then balance it out with the changes. Now this term here, this is your settling from layer 2 down into layer 1, and then your loss from layer 1 or gain across your sediment bed interface due to bed load. And then let's see, what else? Anything else in this one? Nope. So we've got bed load. Yeah, see, so this term here is all for layer 2. So this is your stuff coming in from the top. Following, we got pore water exchange. The QW and Q, these are effective velocities of your groundwater source term, which is applied at the bottom, but it assumes, whatever, because of water's incompressible. If you put in 2 meters per, or 2 centimeters per second at the bottom, you got to get 2 centimeters per second out the top. So the QW is constant throughout your sediment column, but then you've got a diffusion term here also. Then it can be plus or minus depending upon what's going on at the time it's computed. It looks at this term here is, let's see, one's gaining and one's losing. Yeah, so this is the max. So this is an upward flowing system here from the sediment bed. So this is adding constituents to the sediment bed. But if the net transport or advection is downward, then it's adding it to the sediment bed from layer 1. So that's the process by which we account for the pore water diffusion and advection process. Bed load. The original EFDC model had a different approach for bed load concentrations and toxics. Actually, it didn't track concentration of the bed load. What it did is it calculated the net erosion and deposition to and from bed load and advection, and then put it all back in the bed at the end of the time step. EFDC Plus has changed the way toxics is transported in the bed load. We manage a bed load concentration. So as material, just like any other unit volume or control volume. So I have a bed load concentration and a bed load sediment mass, and I have a bed load toxic mass in each square meter. And as material is coming in and going in and out from the bottom through erosion and deposition into the bed load term, I add and subtract to my concentration in the sediment or in the bed load layer. And that just kind of tracks with your sediment in the bed load. So the units here are in milligrams per meter squared, just like they are in your bed. But this concentration here actually represents the bed load concentration. So, you know, your bed load goes up and down, and based on shear stress that's and flows that are occurring at the site. So your bed load concentration may be going up and going down, but at the end of the run or at the in a quiescent condition, everything goes to zero, and it's all being tracked with full mass balance. And that's one of the ways we now can get mass balance with even when you add bed load to the transport for toxics. So this is somewhat of a new approach for calculating bed load concentration for toxic transport. Yeah, it's a totally, right, it's just a computational layer. It doesn't have a layer designation. It's just its own discrete array, essentially. Well, that's a good point. No, it is computed. If I'm interested in knowing my grams per meter cubed, I need to know the layer height. But if I'm only interested in the number of milligrams per square meter, I don't care if it, the bed load layer is this thick or this thick. The concentration would be different, but the mass per unit area is the same. And we actually ignore bed load height in this process. We're tracking mass. And I mean, you can calculate the bed load height. That's useful when you're doing the well, these terms here, this Q here, this is the mass in grams per second. Well, actually, it's grams per second per meter in the x direction. Then you multiply it times your width. But I don't have a height of my bed load in this. Right. Just so the product of this is grams per second for sediment. then I do my fractionation so I know how much of the concentration is moving with that sediment. And that's how we do it now. And then these two, the last term is the bedload loss and gain to the sediment bed. There's no loss of material from bedload to the suspended load. That doesn't happen. It either stays in bedload and then deposits, or under the bed, or just going to stay in bedload all the time. But it'll always deposit as the shear stresses drop. Really messy. It's just an upwind scheme for solving the advective diffusion equation for the pore water transport in the sediment bed itself. I just threw it up here. Not going to explain a lot, except for the fact that this is a delta term here. It's either 0 or 1, so there's a lot of zeros and 1, depending upon if it's K. If the layer is at the top, it's 1, and if it's, it's 0 if it's at the top. So it basically is just looking at that delta, so when it gets to the top, it just throws away that top layer in the actual calculations. And again, you've got your min and maxes for the directional components of the your pore water fluxes. The phi here is porosity in the sediment bed. And so that indicates, obviously that's the amount of water that's available in the pore spaces. And enough of that. Let's talk a little bit about loss terms now. There was a bulk degradation capability in EFDC for a while, but of course it only worked with didn't work with the Sedzel-J model. Now it works with both. I didn't really describe that. That's a point that I should have probably put a slide up. Make a note of this. This is something that we need to discuss. EFDC, original EFDC layer scheme, numbers from 1 at the bottom to KB at the top. And so your sediment is distributed somewhere between 1 to something KB or less, but the numbering scheme, is, from 1 to the top. And then Sedzel-J, that's reversed. But we needed to be able to use the same code. I didn't want to have to write a whole bunch of new subroutines to handle all this this reversal. So there's two things that we've done to address the way Sedzel-J handles or enables it to handle toxic simulation. The first thing that we do is we collapse the active layer into the deposited layer. And we do that because the active layer is usually so thin that from a toxics transport perspective, we don't think it really is a driver. So especially if you've got pore water diffusion and particle mixing in there, what's in that really super thin active layer. We're literally talking, 2 to 3 times your D50 value. So it's really, really small. So we take that active layer component and we add it to the deposited layer. And that becomes the new top layer. Then, if there's any empty layers in between layers 1 and 2, and the actual in-place initial condition layers that were measured, we collapse them all down so that you end up with a contiguous sediment column with no gaps in it. So now we have a sediment column that is contiguous, but it's still numbered going from 1 at the top to KB at the bottom. So it's reversed. So in all the routines in EFDC where we loop over the sediment layers, we just reverse the indices. So it still solves the solutions appropriately, either from the surface to the bottom or from the bottom to the surface. It's just the numbering scheme is reversed. So that's kind of what we have done to address some of the layering issues so that it works with toxics without having to rewrite a whole bunch of new subroutines or redo the way Sedsel J does its layering. So, yeah. Yeah, it was actually not too difficult to do the layer collapse. And then, but you have to, the other thing you've got to do with toxics transport is, as Sedsel J is borrowing and depositing material between layers, that all has to be accounted for in the toxics model. So as the sediment, as the active layer thickens, it's got to move sediment up, but it also has to move toxics up. And then as it thins, vice versa. So that's all, again, accounted for now with the new toxics model in EFDC+. So let's get back to bulk degradation now. So this was in there, but we have added basically a limit so that you can just kind of put a depth limit. You probably don't necessarily want to apply the same bulk degradation rate at the surface as you do at the bottom. Now you can't have multiple bulk degradation rates for the same column. That's not available right now. But you can put a limit, and it will only apply the bulk degradation as long as the depths, the total depths from the surface down, are less than or equal to the Dmax value. Now biodegradation, pretty much the same set of equations, other than the fact that now K is a temperature sensitive coefficient. And we're following this Q10 is a, this is following the WASP 7 and 8 approach for calculating temperature dependency of your biodegradation rate. And you'll notice that your temperature is, you subtracted the 20-degree reference temperature, but then you divide that coefficient, your exponent rather, by 10. And then they have a range. This is a user input parameter, and they give you a specified range and a default. And that's the approach. So it's a little non-standard from, most of your kinetic routines don't use the Q10. I'm open to suggestions. That's just what WASP was using, and we were using WASP as a guidance here. So anyways, I'm open to suggestions and input. But that's what we do. And then it has the same depth limit for application here. Now, as far as the temperature goes, this temperature right now, there's only a single temperature available for the sediment bed. If bed temperature is not simulated, so it doesn't vary, it just uses the temperature of layer 1 from the water column above. If temperature, we'll talk about this with the user interface, if temperature is not even being simulated at all, but you need it for toxics work, temperature can be externally specified just like the DOC values that we were talking about. So you don't actually have to simulate temperature still to have its effect included in the model. And I'll show you that when we get to the user interface. Lastly, we added the volatilization term to EFDC. So your basic volatilization equation here, this is your net transfer rate, and then your depth essentially this is your layer thickness of your top layer. Then you've got your atmospheric concentration, Henry's law, and some the fractions. Is it dissolved in? Because you can only volatilize the dissolved fraction. You can't volatilize the sorbed fraction. So, anyways, that's the basic equation. So the approach that you have to do is you've got a stepwise approach. First, we have to determine what this kV is, and this kV is a function of the inverse of this resistance at the liquid. This is using, I forgot the actual reference name. It's a two-layer film theory for calculating volatilization. That's what's used here. And so we have two films that have a certain resistance to mass transfer across that film. One is the film at on the liquid phase, and there's a resistance term there. Then there's a film on the gas phase and a resistance there. So as the resistances go up, because this is the inverse, your mass transfer rate would go down. And that is equal to this term here, which is this is your transfer rate across the liquid, and this is your transfer rate across the gas, and then the whole thing is inverse, so that everything is, your transfer rates are inversely proportional to your resistances. Now, volatilization depends upon turbulence. And so right now, we have just implemented a relatively simplistic approach for making that determination as to which appropriate set of equations we need to use for the volatilization calculation. So what you do as a user is the user is going to specify a maximum depth and a maximum velocity. And it will use whichever condition occurs will trigger the either the material or the cell to be treated as a quiescent or a lake condition, or be treated as a riverine or a more turbulent condition. And so using these two toggles, the way it'll work is that if the velocities are real high and the depths are real high, if you trigger the high velocities, even though the depths are high, you'll end up down in river conditions. So, it'll use whichever value is kind of controlling to toggle it between the two conditions. Then, once you have identified how you're going to treat that particular cell, then if it's turbulent or riverine conditions, we've got three different options for calculating your liquid film mass transfer rate. So if the depths are less than 0.61 meters, it's going to use Owens. And U is just a depth average velocity and total depth. And then you've got this criteria here. If it meets this criteria, it'll use O'Connor-Dobbins. And then finally, anything that doesn't meet these two conditions will use Churchill and calculate the liquid film transfer rate according to this method. Gas transfer coefficient in a turbulent condition is set to a high value, just because we don't want it to limit the mass transfer. In a quiescent condition, there are two options available, and these are user-specified options. So this is not on-the-fly toggle. This is you as the modeler will make this decision. The O'Connor approach, where we're calculating the liquid film mass transfer rate using Schmidt numbers here, and the gas transfer, mass transfer rate here using viscosity and Schmidt numbers and von Karmans, and then down here it shows you how, you know, these are calculated. These are diffusivity in air and diffusivity in water. Approximations. Obviously, this is just some crude approximation of these diffusivities, but that's, I think it's probably accurate enough to, given all the other processes that are given in the model, to be fairly, you know, within the margin of uncertainty. W10 here is that's your drag coefficient at the surface of the water, and it's a constant right now. It doesn't vary. It's something we might think about varying, but and this is the wind speed at 10 meters. Option 2 is the McKay and Yoon approach, and basically, again, it still uses the Schmidt number, the shears. So you're calculating your liquid mass transfer rate and your gas mass transfer rate according to these equations based on some shear stress toggles. And when you get finished with that, we have all the terms that we need. We pop it back up. Oh, I didn't mention this. The result of this calculation. So now we've gone through all this, the different, you know, quiescent, turbulent, you know, depths and McKay or O'Connor. So we have all these terms. We calculated kV, but that kV is at 20 degrees. So now we have to correct it to your actual temperature according to this, and this is the actual term that gets used in this equation when we actually calculate the amount of mass leaving the system or coming in. If CA is not 0, this could be a source term for if you have atmospheric dissolved concentration, not deposition, but just atmospheric dissolved or atmospheric concentration that's not particle active, and then it will actually add concentration to your water column. Volatilization. I found a series of, I guess they're bugs. I'm not sure. Anyway, some equations that were in one version of EFDC I was looking at, and they kept missing the 1 on some of these divisor. These equations as shown here have come. See, is this the WASP guidance document that I got these from, or did I ended up? No, it was the WASP document that was wrong. That's what it was. The WASP 6 document is wrong. If you go back to, see, where did I? Trying to remember where I actually finally ended up getting the definitive values. But anyways, that's what it is. Beware, the WASP 6 document has the wrong exponents on the equations. And I think it was, it was almost exclusively for the H term, but I'll have to go back and look to see exactly where it was. But if you guys, you find some other documentation and you think I'm wrong, let me know. But I believe that these are correct based on the. Oh, I know what I did. I went back to the O'Connor-Dobbins paper of like 72 or something, and was just looking at the original paper, and that's where I got 2 or 3 of these, anyways, fixed. So that said, that pretty much does the loss term. So now we finished it. We have now just finished one time step. We only got a couple of million more to go, so I hope you guys aren't too busy here. We've advected, diffused, settled, eroded, deposited, pour water diffused. Now we've decayed, and now we've lost done our lost terms at the surface, and ready to do it all over again. Before we move, this is the end of the kind of the theory section.